Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, we are going to go over the graphing of logarithmic functions. Last time we did the exponential functions, so we are going to do the logarithmic functions now. You have to understand that logarithms and exponents are inverse functions of one another, like the square and the square root, like the sine and the arc sine, like any graph or any function that has an inverse. For a function to have an inverse, I don't know if you learned what's the meaning of one-to-one function. I don't think so yet, but that's not the issue. Well, in a nutshell, remember that we said, how do you know a function from a relation? Yes, you apply, if you have a graph, you apply the vertical test, right? The vertical line test, and you see if this line intersects the graph in more than one point, it's not a function. Well, likewise, you can think of it as a horizontal test. If a if a horizontal line intersects a graph into more than one point, then it doesn't have an inverse. I'm sorry, I shouldn't say it has. It's not a one-to-one function. We'll talk about that in more detail, probably in another video. But there is something interesting about inverse functions. Notice we are talking about the logarithmic functions, but just because we did the exponential last time, and the exponential and the logarithmic functions are inverse functions, we have to say that. We have to say that for any two functions that are inverse to each other, the line y equals x, which is a straight line passing through the origin and has a slope of 1, is an axis of symmetry. So it's like the two, if you place a mirror, both graphs would be inverse or would be mirror image of each other, image of each other. So today, as I said, we are going to talk about logarithmic functions and how to graph them. So if you remember the logarithm, we write it as log to some base of some number. So for example, I want to plot a logarithm to any base b, okay? We say if b equals 10, that's the common function, the common logarithm, we just don't write it. We say log x. And if b equals e, we say natural log of x. Okay, so this is just like a vocab, or you're learning new terms. If you, and most likely you already covered that, but what I'm saying is, if you're new to logarithms, that's what. So when I say, maybe we'll need that, I don't know. If we say logarithm to the base b of some number a equals c, that's another way of saying b to the power of x, b to the power of c, why did I say x, equals a. So this number is the base raised to the power of the right-hand side. So how do we plot logarithms? We can take an example. Let's say I want to plot y equals log to the base 2 of x. That's exactly the inverse of y equals 2 to the x. Remember how we plotted y equals 2 to the x? If you remember correctly, here is the x, here is the y, and we say that this graph will always pass through the point 0 and 1. 2 to the 0 equals 1. So 0 and 1. So for the graph of the logarithm, we switch these. It will have to pass through 1 and 0. Then 2 to the 1 is 2. So at point 1, I will get 1 and 2. So here, we are going to do the mirror image, okay? So I will get, we said we switch the x and the y, so we get 2 and 1. And then you see that this graph goes quickly up to infinity, and here it's asymptotic with the x-axis. If I place a mirror image here, then the branch that goes from 1, 0 to negative infinity is the same as the line that comes from negative infinity to 1 and 0. And if you plot it to scale, then the line y equals x, meaning a line that makes 45 degrees with the horizontal, roughly, here would be the axis of symmetry. And some people, you know, they draw the exponential graph and then they took the mirror image to find the logarithms, but you really don't need that. A quick way to plot that is to do a graph. We know that log to any base of 1 equals 0. Why? Because any number raised to the power of 0 equals 1. So here, if x is 1, log 1 is 0. Okay? If x is b to which power would give me b? To the first power. That's why this point, we said it's 2 and 1. 2 is the b, the base, so that has to be 1. B squared is 2. B cubed is 3, and so on and so forth. So this, if I'm plotting this, that b would be 2, 4, 8, 16, 32, and so on and so forth. So the graphing of log to the base 2 of x is pretty straightforward. Now, what if I give you a transformed graph, which, for example, would be y equals, let's say, negative 4 log to the base 2 of x plus 3 and maybe plus another 5. Notice here that would be, so I write b squared, b cubed, but for this example, it's 2, 4, 8. So far, so good? Remember what we did last time with the exponent function. We said, I'm going to take log to the base 2 of x plus 3 and leave it as the right-hand side. Nothing else goes to the right-hand side. Okay, so I want this to be log to the base 2 of x plus 3, which means I have to subtract 5 from both sides and then divide by negative 4 both sides. So this is the way we are going to see what happened to the x, what happened to the y. Notice, this is x plus 3. So really for the x, I have to subtract 3 to make that an x, meaning move to the left 3 units. I'm done. Mathematically, I just subtract 3. So the 1 becomes -2, the 2 becomes -1, the 4 becomes 1, and the 8 becomes 5. It's that fast. But what did I do to the left-hand side? First of all, I have to multiply by -4, right? Remember, multiplying by -4, meaning multiply by 4 is like you are stretching the y by a factor of 4, and then multiplying by -1, meaning reverse or make it reflect on the x-axis, okay? So mathematically, multiply by -4, meaning stretch by a factor of 4 and reflect. This is not x, this is times, okay? Multiply by and reflect over x. Notice when I fill the table, I don't care. This is an explanation to my teacher, but that's what I do. I'm going to multiply these numbers by -4, and then I'm going to add 5, meaning I'm going to move the graph 5 units up. See how easy it is? And you can see by multiplying by -4, you can either stretch, then reflect, or reflect, then stretch. It doesn't matter. Because here, I can multiply by -1 and then by 4, or I can multiply by 4, then by -1. So some cases, the order is not important, but in other cases, it is. So let's do that. The 0 times -4 is still a 0, and then I add a 5. By -4 is -4, plus 5 is 1. By -4 is -8, plus 5 is -3. By -4 is -12, plus 5 is -7. And then you can plot it. Let's do that. Let's do that by plotting. Oh, here I have to tell you something. Well, there is a way, but if you want to enter log to the base 2 in your graph, you don't have log to the base 2. So I think I mentioned that already in previous, it doesn't matter, previous videos. I said, if you want to say log to the base 2 of any number, let's say 7, and you don't know how to do it in a calculator because you don't have all the possible bases, it's impossible, right? So we say, I can say this is log 7 divided by log 2. So the log to the base 10 of a number, because we have a log button. So I can say log 7 over log 2. So divided by the log of the base, the one on the top over the one at the bottom, or natural log of 7 over natural log of 2. And both are correct. So here, oh, why do I have a square here? I clicked the wrong one. Okay, so the function, I want to enter this function. I can enter it as -4, and then I'm going to multiply either by log or natural log, it doesn't matter. So I'm going to say log of x plus 3 divided by log of 2. Remember, because we have 2 is the base. Did I enter -4? Okay, I forgot if I multiplied by -4 or not. Why do I have an extra? Oh, because the log opens one and I opened another. So I just don't want to make sure it's correct. And then I add a 5. If I go, oops, sorry. If I go to the window, I want the window to be the x less than 2. Well, -4 is okay. And the maximum is at least 5, so let's make it 6. The y is from -7. Well, -10 is fine. 5, let's make it 6. And let's graph it. So here is the graph. Okay, let's look at the table. At -2, I have 5. At -1, I have 1. At 1, I have -3. And at 5, I should have -7. Yes, -7. So it's correct. It's very simple. Very simple how to do the transformation, and we can plot it. Well, I was bringing a graph paper to plot it, but I think it's going to be easy. I don't know. I don't want to waste your time on that. Let's take another example and maybe we plot that. So in this example, I'm going to say y equals, let's take log to a different base. So let's say base of what? Or 10, base of 10. But now I'm going to say 4 minus 2x. Okay, I'm going to say let the x be negative, or the coefficient of x, and then maybe plus 3 or minus 2, whatever. I want to plot that. Well, the parent function is y equals log of x. And if I want to have a table, I see that, again, x and y, if x is 1, y is 0 always for the parent function. And then when x is 10, 10 to the 1 is 10, 100 would be 2, 1,000 would be 3, but we cannot get, well, we can say, notice that I cannot have a log of a negative number. Well, I shouldn't say that. We can have a log of a negative number, but the answer would be complex number. It won't be a real number. So it will have i's and a real portion and an imaginary portion. But somewhere in between, we don't know. So 0, 1, and 2, I cannot, well, I can say 1,000, and that would be 3, right? But it's really going to be very large. Now, when I ask you to do the same method we used before, then we have to all what we have to say is y minus 3 equals log of 4 minus twice x. Right? That's how you do it. We talked about that several times. Let's start with the y because the y is trivial. For the y, I'm going to add 3, meaning move up 3 units. That's it. Now, when you look at the x, here, I want to show you that we can do a lot of stuff. For example, I can factor the 2 out, and that would be 2 minus x. And then I'm going to multiply by -1, meaning I take the -1 out, and I will have x minus 2. Or I can divide by -2 directly and make that x minus 2. So you can see the first step, I can say, I'm going to rewrite that as -2 times x minus 2, right? -2x plus 4. And that's pretty much the easiest thing. So how do I make this x? I could have said subtract 4, meaning move 4 to the left, then divide by -2, which means reflect on the y and shrink by a factor of 2. No, I don't want to do that. I want to shrink. So I'm going to divide by -2, meaning shrink by 2, by a factor of 2, then, or before, it doesn't matter which one comes first, then reflect on y. And then I'm going to add 2 to the x. So add 2, meaning move 2 units to the right. Notice that it would be completely different if I move 4 to the left and then divide by -2 and then shrink and reflect. So if I reflect first, I'm going to move 2 units to the right. If I reflect last, I would move 4 units to the right. and then switch. Here I reflect it first, then move 2 to the right, or move 4 to the left, then reflect. So it will go to the right because I'm going to shrink the x by a factor of 2. It really is the same thing, but you have multiple ways of looking at the same equation and tell me, oh, I can do it by shrinking and reflecting and moving, or moving first, then shrinking, then reflecting, or there is a lot of stuff to be said. Remember, we had rules that if you have translation and reflection, you have to reflect first and then translate. No, you don't. You really don't. Notice that if I had divided this whole thing, I'm sorry, if I had subtracted 4, meaning move 4 to the left, and we can do that. Let's do that. So I'm going to call that x2. So this is x1 and this is x2. Let's write x1, x2, and y. So for x2, I'm going to move, subtract 4, meaning move 4 units to the left. So that would leave me with -2. Then I'm going to say divide by -2. Notice if I divide by -2 first, I move 2 to the right. But if I move first, I move 4 to the left. And let's see if we get the same stuff. Again, this would be the same shrink by a factor of 2, then reflect on y. Let's do the math. So the y, just add 3. So this would be 3, 4, 5, 6. If I use x1, I'm going to divide the x by -2. It would be -1/2. Then I add 2. It would be 1.5, 1.5. I'm going to divide by -2. It's -5. Then add 2. It would be -3. Divide by -2 is -50. Add 2 is -48. Divide by 2 is -500. Add 2 is -498. What if I do that? If I move 4 to the left first, the one would be -3. Then I'm going to divide by -2. -3 by -2 is 1.5. Subtract 4, it becomes +6. Divide by -2, you get -3. You see, it's the same thing. But you wouldn't know that if you used, the rigorous, very rigid rules in your book. When you see it this way, it means you move to the right. If you see it this way, it means you should. No. You have many ways of doing it. I can move 2 to the left. So it becomes 2 minus 2x. Then I divide the whole thing by -1. It would be 2x minus 2. Then I'm going to add 2, meaning move 2 to the right. And then divide by -2, shrink and reflect. I can do whatever I want as long as my algebra is correct and I will end up with x at the end. Let's continue. We said 100 minus 4 is 96, and 96 divided by -2 is -48. 1,000 minus 4 is 996. Divided by 2 is 498, and -1 would be -498. Let's make sure this works. I'm going to go back to my plot, but this time I'm going to say natural. I'm going to use natural log instead of log to show you that it doesn't matter. Both of them are correct. Natural log of 4 minus 2x divided by natural log of 10, because if it's a log, I don't need to do anything. The log is base 10 and this is base 10, so you don't need to change anything. And that's why I use the natural log here. 4 minus 2x plus 3. For the window, of course, now it changes because the x goes from -500, say, to +3 or 2. The y goes from 3. So we can say 0 to 8 or something. It doesn't matter. And here is the graph. Of course, you won't see exactly how it's looking, but let's go to the table and see what do I have at. I don't have 1.5, but we can get it because we can always we always can click the plus, and instead of increasing by increment by 1, I make it 0.5 so I can see the 1.5. At 1.5 is 3. At -3 is 4. At -48, or you can just type it down. I think it's easier. -48. Let's go to second calc, a value. I want x to be -48. The y is 5. I want it to be -498. And I get y is 6. Again, I didn't plot that, but it would be ridiculous because of the 500 and the. Maybe I get one last example. I wanted to give you another example. Let's see what we did here. So this time I'm going to make a fractional base. So I'm going to say try log, say to the base 1/5 of x minus 6, and I can add also a -2, whatever. Y equals that. You say, what is the fractional base? We'll see. So the parent function is y equals log to the base 1/5 of x. So for the parent, here is x, here is y. Again, if x is 1, y is 0. But how do I make x, how do I make y 1? 1/5 to the first power equals 1/5. So if this is 1/5, I get 1. 1/25 would be 2, but how can I plot that? It's going to be very tough. Here, because the base is negative, what if I raise the base of 1/5 to a -1? Won't I get 5? So when x is -1, I get 5. When x is -2, I get 25. And when x is -3, I get 125. Let's even do that. Okay, so when you have a fractional, in fact, I should have plotted both to see that the y-axis, let's do this. I'm sorry. I just want to show you this. So for this example, because it's already there, if I go and say, now plot, oh, but I have to do e to, no, I can show it to you here. This thing. Let's say I'm going to clear that. For this example, I'm going to do log of x over log of 2. And then here, I'm going to do 2 to the x. And then here, I'm going to do y equals x to see if it's a mirror image. Maybe the numbers we had, the lowest x was -2. So I can say -3 or 4, -5. And the highest x was 8, so let's say it's 10. For the y minimum is -7, so maybe -10 again. And the highest was 5, so let's make it 8. Oh, it's already 8. And now I'm going to plot them all. Here is the natural log. Here is the exponent. and here is y equals x. And of course, if you want to zoom and make it square 5 so that you get the same scale. Well, I think it was the same scale. Yeah. Do you see now that the y-axis, this one is turning to the right, and this is going up, this would be going down, and this would be going to the left, and it's exactly a mirror image. Now, let's go back here and do this. I'm going to leave log to the base 1/5 of x minus 6, and then I'm going to add 2 to both sides. I get y plus 2. For the x, I'm going to add 6 or move 6 to the right. For the y, I'm going to subtract 2 or move 2 down, and that's it. So that was easy. Meaning, here is my new function. For the x, I'm going to add 6, so I get 7. 7 and a fifth, or 7.2, 6, 5, 4. For the y, I'm going to subtract 2. -2, -1, 3, 23, 123. So let's plot that. So I'm going to clear this and clear that and clear that. Well, here I'm going to say log of, clear, log of x minus 6 divided by log of 0.2, which is the 1/5, minus 2. I want my window to go from, say, -5 to 130. No, I'm sorry, that's the y. That's the y. -5 to 130. But my x, the smallest is 4. So let's say from 3 to 8. What happened? Did I enter a wrong window? I said the x from 3 to 8, and this is from negative something. Yeah, what happened? Why it's not showing? It's taking forever. Okay, I don't care much about the graph really, because the numbers were. So I have to go to +7 for x. All of these are errors because you don't have negative values. But when I go to over the 0, in fact, over at 7, see 7 and -2. For 7.2, let's leave it for now. If I go to, when I go to, I did something wrong. I add 6. So when I add, for the x, I was adding 6. Why did I add? This is 6.2. And this is 5. Something is wrong. That would be error. What did I do wrong? I subtracted 2 from this. And I added 6 to that. Did I enter the equation correctly? Can be. Did I enter the equation is log x minus 6. Yeah, it is divided by log of 0.2, which is 1/5 minus 2. So how come I'm getting a weird thing here? So if x is 7, I get -2. If x is 6.2, I'm getting -1. That's not, I don't see a -1. Does it say -1? Oh my God, this is crazy. 6.2. Yeah, I get a number. So why, if x is 5, no, it's saying, yeah, because 5, it would be, That's crazy. That is crazy. These have to be negative. It cannot be negative values. 1/5. I reverse the x and the y. I'm sorry, guys. Okay, x and y. So if x is 1/5, I get, if x is 1/5, I get 1. If x is 1, I get 0. Of course, x cannot be negative. If x is 5, this is negative. I reverse the x and the y. I'm so sorry. I don't know how I did that. So when I go to the x and y, I add 6 to the x. So this is 6.2. And then this is 7. This is 11. This is 31. This is 131. For the y, subtract 2. Okay. Okay. So when I go to the window, I want the minimum x to be, say, 0.2. I don't want 0. No. That's, yeah. 1/5 to the -1, 1/5 to the -2, 1/5 to the -3. And then when I added 6, I got those. Okay, so for the x, I want to start with 6.2. So let's say 6. And then I go to, say, 135 or something. And for the y, I go from -6 to -1. Yeah, now I have the graph. I'm so sorry. I don't know. It's like I messed it up. Okay, here is the graph. And again, if you want to go to the table, you can see that at 7, you get -2. At 11, you get -3. At 30, oh, no, I have to go to a value of 6.2, I get -1. At 31, I get -4. At 131, I get -5. Sorry, guys. But I think it should be pretty straightforward how you go from, the parent function, this is, you say, how do I return back to the parent function? And that's exactly what happened in the transformation. We ended up with like roughly 40 minutes because of the, but at least we did 3 different examples. We show how we rotate about x or y, how to stretch or shrink. What if we have a base that is fractional? And I hope the rest was easy. Again, please forgive me for this horrible error that I made. I used the -x, which is impossible. We don't have, right before that, I said we don't have natural log of a negative number, or else you will end up with complex value. Okay, so again, if you have any questions or anything was unclear, please let me know by dropping a comment in the comment section, and I will do my best to get back to you as soon as possible. Thank you very much, and hope to see you soon.